Okay, for z cubed equals 1, we know that there must be 3 roots, and all the coefficients are real. There's no complex coefficients in that polynomial. So we know if there are conjugate roots, they have to come as conjugate pairs. Sorry, complex roots, they have to come in conjugate pairs. So we know here that obviously 1 would work. So 1 is the real root, one of the real root of z cubed equals 1, and alpha and beta will have to be conjugates of each other. Another thing we know straight away, if we're just looking at this, is that if you think of, if I put minus 1 over that side, if we factorize, it's very easy to factorize this kind of polynomial, you can see this is what we get. So if we know that z cubed minus 1 equals 0, so let's make that equal 0, you can see one of the roots, the real root, will be 1. So that's one of the roots. The other 2 roots will have to come from here. So, and we've already been told that the other 2 roots are alpha and beta. So alpha and beta are going to have to work in here. So we can see that alpha squared plus alpha plus 1 has to equal 0 for it to be a root. We also know that beta squared plus beta plus 1 will equal 0. So actually that gives us part C already. Okay, so let's look at part A. So basically we are told that alpha is one of the conjugate roots. So let's say alpha is a root. So clearly if we sub it in, it has to work. So for example, alpha cubed equals 1 or alpha cubed minus 1 equals 0. Now if we take conjugates of both sides, now the conjugate of 1 is just 1, of course, and we can also write it this way, same thing, conjugate of alpha all cubed equals 1. So you can see there that alpha, no, the conjugate of alpha has to also be a root. And since we know there are only 2 more roots, the alpha and the beta, then beta must be equal to the conjugate of alpha, since there are only those 2 complex roots. All right, so that's our A. When we're looking at our B, part B, let's just get rid of all of that. So we know a couple of things. We know that alpha is a root, so alpha cubed will have to equal 1. We also know that the conjugate of alpha is also a root, so that's going to have to equal that as well. All right, now let's look at the roots alpha and beta. So we know that if I have a look at alpha times beta, that's beta there, if I cube that, that is the same as alpha cubed beta cubed. Now beta is, we know, just the conjugate. So let's say of alpha, so conjugate of alpha cubed. And that also equals, I should have written alpha, it doesn't matter. All right, and that has to, of course, equal 1. Don't know why that didn't rub out. That because we know alpha cubed is 1, and we know that alpha conjugate of alpha all cubed is 1, so 1 times 1 is 1. So yeah, let's use that. So here we've got alpha cubed, I'll just write it over here. So we've got alpha cubed times alpha, well, let's cube root, let's do that. We know that equals 1. If I cube root both sides, I've got alpha times conjugate of alpha equals 1. We also know that, of course, 1 is equal to alpha cubed, so actually I might write that here. All right, if I divide both sides by alpha, of course, alpha could not be 0, otherwise I can't divide it by alpha. But if I divide both sides by alpha, I get that alpha conjugate of alpha is alpha squared. So that really gives us that beta equals alpha squared. Or if I go back to here and I divide both sides by conjugate of alpha, and that can't be 0. So if I divide both sides by the conjugate of alpha, I will get, let's go back to a better pen, maybe. So if I go back to alpha times conjugate of alpha, it also has to equal conjugate of alpha cubed from here. So if I divide through by the conjugate of alpha, I will get the conjugate of alpha squared being alpha. So that is the same as alpha equaling b squared. So I've got alpha equals b squared, and I've got beta, or alpha squared equals beta, both of those. So that's part B. All right, so part C we've already looked at. Let's look at part D. That's the interesting one. So the sum of the first n terms of this series has to either be 0, 1, or negative alpha squared, depending on the remainder when n is divided by 3. So the n terms, so let's think about the, summing up n terms here. N terms. And let's start with, if we had a remainder of 0. So to get a remainder of 0 when we divide n by 3, that n would have to be some factor of 3. So let's say 3m. So let's make n equal 3m, then we'll get a remainder of 0. So if you think about it, for example, if m was 1, I just want the first 3 terms, and I've got 1 plus alpha squared, which we know from here, 1 plus alpha squared is 0, so that would be 0. So let's look at the, let's make m equal 2, so we'll keep going, and we're going to have alpha cubed plus alpha to the 4, alpha to the 5. So actually, if I factorize them all by alpha cubed, I get 1 plus alpha squared. That's what the next lot would look like. The next lot, of course, would be alpha 6, 1 plus alpha squared. So you can kind of see a pattern here. So if we kept going, we would, I just got to go down here. So we get alpha cubed to the power of, let's say m there, and we get 1 plus alpha squared. So we'd get, each time we're just doing blocks of 3 because this n is divisible by 3. So you can see that that is always going to be, because 1 plus alpha squared is 0, and then we're going to get 1 times 0 because alpha cubed is 1. Now this is alpha to the 6 is alpha cubed squared, so again 1 squared times 0. So always, even when we get up to here, we're still going to get 1 times 0. So we're always going to get 0. So if it's if n, the number of terms, is divisible by 3, then when we sum them, we're always going to get 0. So let's have a look at when it's divisible by, when we divide it by 3, there's a remainder of 1. Let's have a look at that one. So let's make, for example, n equal, so it's divisible by 3, but then there's a remainder of 1. So let's make n equal 3m plus 1. There are 3m plus 1 terms. When we do that, let's see what we get. So for example, if I made m just 1, we would take the first 4 terms. So we're saying 1 plus alpha squared, and then we're adding alpha cubed, so that's always going to be 1 more. Now alpha cubed, remember, is 1, so I'll just show you if I do that. So you can see if I just had m equal 1, I would get 0 plus 1, so I just get a 1. Well, let's try if m was 2, so that's 7 terms. So we'd still get that 0, and then we'd get the next 3 terms. So I'll do this again. And then we're going to get the next term, which will be alpha 6. So again, if you think about it, you've got 0, alpha cubed is 1, so 1 times 0, so still 0. And then you get 1 for alpha cubed squared, or alpha to the 6. So you can see you're still going to get 1. So it looks like we're always getting 1 this time. Let's just do it for the general case, where m equals m. So we're going to get 1 plus alpha squared, and then we're going to get, again, alpha cubed times 1 plus alpha times plus alpha squared. And then alpha 6, 1 plus alpha squared. So let's keep going all the way up to, so remember we're always going to have that odd term. So the last term is going to be some alpha cubed, it doesn't work down here, the silly pen, to the power of m. So some power of alpha cubed. And you can see we're going to get 0, 1 times 0, 1 times 0, all the way up to 1 to the m, which is 1. All right, so if there's a remainder of 1, we're always going to get a 1 when we add those terms. All right, so let's look at a remainder of 2 now. So let's make our n be 3m plus 2. So when we do that, if I just move this up, so far think about it, if we've no remainder, we add them all up, we get 0. If there's one remainder, we get 1. And now we've got n equals 3m plus 2. So we're going to go all the way up to m terms, where m equals m, I should say. So we're going to kind of keep going along like this. And then we're going to, if you think about it, we're going to have 2 terms left at the end. So we've got our 1 plus alpha, but not plus alpha squared, just a 1 plus alpha. All right, so again, you can see we're going to get 0, 1 times 0, always 1 times 0, but then we're going to get the last 2 terms. So alpha cubed to, doesn't matter what power, we're going to get 1, and then we're going to have 1 plus alpha at the end. So you can see the only thing left is 1 plus alpha. But remember that 1 plus alpha squared equals 0. So 1 plus alpha is equal to negative alpha squared. So we could write 1 plus alpha, or we could write minus alpha squared, which is, I think, what it wanted. So we go back up and check. And it says, show that it's either 0, 1, or negative alpha squared. So there you go. So 0 if the n terms is a factor of 3. If there's a remainder of 1 when it's divided by 3, we get a sum of 1. And if the remainder is 2, when we divide the n terms by 3, we get a sum of negative alpha squared.